Hello students, welcome back. Let us resume our discussion in section 3. Previously, we completed up to 3.3, but before starting 3.4, let's have a brief recap. Here's a definition of the Moebius function. Given positive integer n, we define the Moebius function value mu of n as 0 if n is divisible by any square of prime. Otherwise, we define it as -1 to the k power, where k is the number of distinct prime factors of n. Here's some examples. Mu of 1 is -1 to the 0 power, so it's 1 because there is no prime factor, 0 prime factors. Otherwise, there are prime factors, so we'll have a prime factorization. And when there's a prime factor with power greater than 1, in other words, 2 or higher, then the first line applies. So mu of n is 0. Now, if there's no such prime factor, in other words, all the prime factors have power 1, then -1 to the k power, so we have either -1 or +1, depending upon whether k is odd or even. That was the definition and some examples. And then also remember that the Moebius function is multiplicative. And finally, remember Moebius summation formula. We proved it here previously. The sum of all mu of d for all positive divisors d of n is either 1 or 0. In a special case, when n is 1, then we don't really have a summation because there's one divisor. Only 1 divides 1 and there's nothing else. So we have just 1 equals to 1. It's not a summation, nothing else. Otherwise, the summation is all 0. If you have more than 1 divisors, and if you do have a summation, always we have to have 0. That's maybe a summation formula. Keep that in your mind, and let us go ahead and prove Moebius inversion formula. Suppose that the arithmetic functions capital F and small f are related like this. Then we can invert into this form. So here, capital F is expressed as a summation of small f. Then small f can be expressed as a summation of capital F modulo mu. Not precisely, but modulo mu, with some adjustment through mu. That's Moebius inversion formula. By the way, before proving this, let's come back to this definition here. Not the definition, this condition, excuse me. Doesn't it ring a bell? Haven't you seen this before? You must have. You saw it in section 1 at least. Right here in theorem 1.5. The same relation, capital F is a summation of small f, and small f is multiplicative, then so is capital F. Remember that? And some of the corollaries. Tau is multiplicative, sigma is multiplicative, and also sigma k in general. Remember all those? So thanks to Moebius inversion formula, small f can be written as a summation of capital F modulo mu, and mu is also multiplicative. So we end up with this conclusion later on. Same condition here, capital F is summation of small f, then if capital F is multiplicative, then so is small f. Go back to 1.5. Do you realize these are converse of each other? Small f is multiplicative, then so is capital F. Capital F is multiplicative, then so is f. So combining these two, what do we conclude? Capital F is multiplicative if and only if small f is, and vice versa. It all comes from the Moebius inversion formula, and that's what we are up to. We're going to prove it. Okay, all right, how to prove it? Okay, let's do this one step at a time. I hope I can do it in a single video. Let's try. First, a setup. These two summations are always the same, in general, regardless of selection of arithmetic functions. They don't have to be mu and capital F. For any G and H, it'll still work out. The reason What do you mean by d dividing n? That means d times some integer delta is n. Consequently, delta divides n, and vice versa. Delta dividing n, that means some d times delta is n, and we get that as well. Or another way to write the same thing, delta can be written as n over d, that's an integer. D is n over delta, that's an integer, because we have this divisibility. Therefore, the left-hand side here can be rewritten as n over d as delta. See, n over d is delta. And then d dividing n, and then delta dividing n are same, so we can rewrite as delta dividing n, same thing. And then d is n over delta. So we get this expression, and finally, just change the characters. Expressed d in place of delta, and we get the final expression here. Because delta and d, they are both dummy variables. We're going to take all those for n and adding up everything anyway, so they're going to disappear anyway. So we can re-express those in terms of d. So we get this, in general. They don't really have to be mu and capital F. It happens all the time. So these two are always the same, so we don't really have to worry about this part. Let's just prove this part. Now, how do you prove that? Well, here, capital F is the summation, so put that in. Then we are going to get this expression. See, capital F, this one I'm highlighting in purple, is the summation. N over d, so all c that divides n over d. All right, like this. And then push mu d inside, and we get the third expression here. So what do we have here? First summation is for d dividing n. Second summation is for c dividing n over d. And then we have mu of d times f of c. That's summation. That's this thing. Eventually, we have to prove this is equal to f of n. And the key technique, the key step, is to switch the order of these two summation. We'll find a way to switch the order. How are we going to do that? Well, that's step 2. All right, let's move on to step 2. Let's have a short digression about the divisibility again. Let's see, d divides n, I'm using blue there, and c dividing n over d, I'm using red there, so let's stick to blue and red. Blue summation, red summation, all right? Now, I don't need this coloring anymore, so I don't want to get confused with these. Now, this blue and red associated to this blue summation, red summation can be put together into this single expression, and then later on it can be re-expanded into c dividing n and d dividing n over c. That's our claim. So that under this claim, let's rewrite this summation. D divides n. Under that, c divides n over d. That's the order. And thanks to this, which we will prove shortly, we can change the order. C divides n, and d divides n over c. Red. I didn't prove it yet, but assuming this is true, this blue summation, red summation, that order, I can switch this into green summation, red summation, thanks to this equivalence. Blue and then red will become green and red. See that? Once you have this, it's easy. Get this f of c out, then summation f of c, and then we have this. Now, we're not completely done yet. Let's see, is it wise to come back and prove it? Yeah, okay, all right. We're not completely done yet, but still, I think it's wise to come back and prove this, because I don't want to get this undone and then move too far away. So let's prove this. So blue and red is equivalent to just red and equivalent to green and red. Let's see, how does that work? So D divides N, and then C divides N over D can be written as D divides N. So N over D is an integer, yeah, blue, and C divides N over D, so N over D over C is an integer. N over D is not a rational number. I mean, it is, but it comes down to integer because D divides N, so N over D is an integer, we know that, blue. So N over D is an integer, so divide C again, so we get something stronger. And then manipulate this, push D to the other denominator, then we get this expression here, and please take a good look at this. This red condition is stronger than this blue. So this red absorbs this, and we just have this. Blue just disappears because we don't need it. It's an absorption law. This is stronger, red is stronger. You see, this is denominator D, denominator C times D. This denominator is multiple of that denominator. So if this is integer, then that's also, this is stronger. This is integer, then always this is integer, but not always the other way around. Now, from the right-hand side, we can work out the same. C divides N, green, and D divides N over C, red. And C dividing N is N over C is an integer. And D dividing N over C is N over C over D is an integer. And exactly the same computation follows. Push C downstairs and we get N over CD is an integer. And that's stronger than this green, so it absorbs this green just as it absorbed this blue. So the conclusion, this blue-red is equivalent to this green and red. Let's go back. D divides N and C divides N over D means C divides N and D divides N over C. That's what we did here. Blue-red, you can rewrite it as green-red. But more or less the change of order, C first and then D later. And then get this f of C out, we get this. We're not done yet. We're still not done yet, but we got closer. How close? Let's use Moebius summation formula. We have summation of mu, so we can use Moebius summation formula. In other words, the summation is 1 for a special case n over c is 1. In other words, c and n are the same, otherwise all 0. So even though we have a big summation for all positive divisors c that divides n, we are multiplying bunch of zeros except for one exception when c and n are the same. Otherwise, they all disappear. For all divisors of n, all positive divisors of n, they all disappear except for the last one, n and c are the same. Consequently, we just get f of n. Isn't that what we wanted? We started from here, and then eventually we got to f of n. That completes the proof of Moebius inversion formula. We went through a number of difficult steps, number of strange techniques, but in the end we got it done. What do you think? Amazingly difficult? Well, I agree. It is. What can I say? It is.